I still remember vividly the time I first met Einstein. I was a graduate student in Princeton, and Einstein was, of course, in Princeton then. And I was persuaded by other people to go in to talk to Einstein about some ideas I was working on. I went in fear and trembling, but he was extremely pleasant, and I was still trembling when he said, "Please write the equations on the board." And I began writing them. And then he said, "Please go slowly. I don't understand things quickly." The unique thing about Einstein was that he never grew out of the sense of wonder that we all have as children. And that sense of wonder, coupled with a passionate feeling that there is beauty in the universe waiting to be discovered, was the main motive of all his achievements.
Einstein's faith in the harmony of nature led him to startling discoveries about the universe we live in. He uncovered fundamental laws and opened the door to the space age.
Einstein was a profoundly religious man, but he did not believe in a personal God. He believed in a God that you could sense by looking at the marvels of the universe. This beautiful instrument is called an orrery. It's at Princeton University. It's 200 years old and a little more. And what it does is to show the motions of pretty well everything in the solar system, at least that was known 200 years ago. Right in the middle, you see the sun. And there you see the Earth with one moon, and you go out, here is Jupiter with 4 moons, and way out here, Saturn with also 4 moons. You can just see them there. And
Banesh Hoffman worked with Leopold Infeld and Albert Einstein. Together they simplified the conceptual framework of the theory of relativity.
Now, Newton, when he made his grand synthesis of the heavens and the earth going according to the same laws, he did it quite differently. There was none of this sort of clockwork gearing and that. Instead, he had an invisible force of gravity from the sun to the planet, from the earth to the moon, and pulling the apple down in the orchard. And this, however, had to have with it 3 laws of motion, and you couldn't have the laws of motion until you had absolute space and absolute time.
Space and time. These are the 2 fundamental ideas of physics. Newton assumed that space and time were absolutely independent. Everything moved mechanically through the heavens against a background of constantly unfolding time and fixed immovable space.
Well, this beautiful sort of disembodied theory was so successful that people thought indeed that there was a sort of celestial clockwork involved here, even though it was nothing like this, but everything worked according to law. And people began speaking of God as the divine clockmaker. Now, the trouble with Newton's system was that it was put into absolute space. And nevertheless, one of the earliest deductions from the laws of motion was that you ought to have a principle of relativity. And this very much upset Newton because it was, in a sense, against the whole spirit of starting out with absolute space.
For more than 200 years after Newton, science continued to build on the foundation of his laws. Yet Newton knew that motion is sometimes relative. Newton's difficulty with the principle of relativity was a fact which would not go away. And Einstein's sense of the harmony of nature would not allow him to forget it.
Einstein worked in this building, and it's probably in this very room that he made a certain statement. The people had been asking Einstein about some experiments that gave unexpected and rather strange results. And Einstein said the following: Raffiniert ist der Herrgott, aber boshaft ist nicht. What that means is God is subtle, but he is not malicious. And what Einstein had in mind was that when you're doing research, you should expect to have difficult problems to solve because of the sublimity of God and the universe. But you should not think that God is deliberately setting malicious traps to mislead you.
While still a young man, Einstein developed a new view of the universe.
In 1905, Einstein produced his special theory of relativity. 10 years later, he produced what's called the general theory of relativity. And according to that, among other things, was a prediction that light from a star grazing the sun would be bent.
Einstein's general theory is about the structure of the universe. To test it, in 1919, the English astronomer Eddington and his colleagues sailed to the coasts of Africa and South America to photograph the sky during an eclipse of the sun. In the night sky, the stars seem to have a fixed pattern. We see two stars a certain distance apart. But what if the sun moves into a position between the Earth and the stars? Einstein had predicted that the gravity of large bodies would affect the space around them. Everyday experience tells us that light beams are straight. Yet Einstein said starlight would be caught up in the distorted space around the sun and bent. The British astronomers photographed an apparent shift in the position of the stars. Light had been bent. Space was curved. Einstein was right.
They verified the bending of light, and when they did so, Eddington said it was the happiest day of his life.
The special theory of relativity is a special case within the general theory and deals with the nature of space and time. Both Newton and Einstein were concerned with how you measure movement.
If you want to measure movement, you have to know a distance gone and a time taken. Newton suggested that we have absolute space, in the sense you could make a mark on it and it would stay put. Then you can make another mark where the thing has gone and measure the distance. As for the time, Newton just assumed that there is a universal time everywhere that is always the same, and so there's no problem about measuring the time taken.
Newton's laws of motion require space to have an almost physical reality. But even so, some motion is hard to detect, and some is undetectable. The principle of relativity is a fact of everyday experience. It was commonly known to sailors long before Newton's time.
Albert Einstein loved sailing, and it may well be that that made him particularly interested in the way things move relative to one another. In a way, we can tell how they're moving just by looking at the surroundings. There's much more to it than that. This cabin happens to have no portholes. I know I'm in the boat, but I don't know whether it's going forward or not. As a matter of fact, no experiment I make in this cabin can tell me whether it's going forward or not. Let me give you an example. Here's an apple. I drop it. It drops vertically. If we were moving forward, or if we were stationary, it would still drop vertically. It wouldn't fall in that direction. This is something we're all aware of. It's called the principle of relativity. In 1905, Einstein made this principle one of the two building blocks of his special theory of relativity, and that theory revolutionized science. I should mention that I'm talking here of observers who are in uniform relative motion, which means moving in straight line with constant speed relative to one another. You know, a lot of people think that relativity has to do with the idea that everything is relative. I wish I knew the miscreant who first called that theory the theory of relativity. Einstein didn't call it that. Actually, it is much more a theory of what is invariant, what is unchanging. And what it says is essentially that if I'm here and someone else is moving relative to me, then we both nevertheless have the same laws of nature.
Einstein's intuition told him that the principle of relativity was fundamental. We have no way of knowing if this object is at rest or if it is in uniform motion. Motion can be measured only in relation to some other object. The idea of motion in a single isolated object is meaningless. These objects all move in relation to each other, but they do not move in relation to an empty space, like ships in relation to the sea. There is no empty, absolute space. There are no fixed reference points anywhere in space. Motion is relative. Absolute space, absolute time. For Newton, time was independent and eternal, as if there were somewhere an imaginary universal clock, and all the other clocks in the universe were synchronized to it. A clock is a device for measuring the order of events. We think of events as taking place in time. Halifax, Nova Scotia. Nearly 5,000 kilometers away, Vancouver. Two events can happen at the same time. But if they are not in the same place, how do we know these events are simultaneous? Two clocks are far apart. We synchronize them with a light signal from the central point. This signal is not instantaneous. Human perceptions are limited. In our everyday experience, we are not aware of any limit to the speed of light. It moves too quickly for us to see it. When we send signals to very distant objects, the time they take to travel becomes noticeable. Radio waves travel at the speed of light.
Come in, Houston Control. Come in, Houston Control.
Events take place in time as well as in space. We cannot know about widely separated events at the same time. The speed of light was discovered by the Danish astronomer Romer watching the planet Jupiter. He timed the eclipses of Jupiter's moons. Later in the year, the distance from Jupiter to Earth had increased as both planets made their journey round the sun. When the measurements were repeated, the intervals between the eclipses seemed longer. The orbit of the moons was not changing. Light from Jupiter was taking longer to travel here. From this, Romer was able to calculate its speed. Later, scientists found that the speed is fixed and constant, no matter who measures it.
As we know, Einstein built on two postulates. Now I want to talk of the second one, which was that the speed of light is independent of the motion of the source. Now, if you believe in a wave theory of light, which was the thing at the time, then this is perfectly obvious. And the reason is this: suppose I start a wave sort of in a pond or in the medium that carries the light waves, which is called the ether. Once I've started the wave, it moves on its own and has no link to what caused it. So it's, shall I say, perfectly obvious in wave theory of light that the speed of light, the motion of light, is independent of the motion of the source. Now you get into trouble for the following reason. If you believe that there is an ether that carries the light waves, then you ought to be able to make experiments that would measure your speed through the ether, and that would let you know your absolute speed in a sense. But according to the first postulate of Einstein, which was the principle of relativity, you're not allowed to know your absolute speed in any sense at all. So we have a really terrible conflict. Now, most people would say, well, all right, we have to throw out one or the other, or maybe both of these postulates. But Einstein had an extraordinary genius. He was able to go to the heart of a matter in a fantastic way. And he realized that the thing to do was to keep both of these postulates in spite of their seeming conflict and resolve the conflict by looking elsewhere and giving up something that we had cherished for a long time. And essentially he was saying time is suspect. Once you have new ideas as to the behavior of time, then in a sense you have created a revolution in science, because pretty well everything basic in science depends on the way you measure time, the way time behaves. What is time? There's no answer to such a question. You can say it's something you measure with clocks, but as to what it is, well, you can't even say what space is, you can't say what existence is, though you have a feeling you know it. These are eternal mysteries. Science doesn't tell us what things are, but only how they behave.
Working from just two principles, Einstein resolved the long-standing conflict in physics. Events that happen at the same time for one person do not necessarily happen at the same time for another. This spacecraft is traveling at very high speed. It has two clocks, one in the bow and one in the stern. In the center is a light beacon. Moving with the spacecraft, we are at rest in relation to it. A beam of light synchronizes the clocks. The clocks are now synchronized for anyone traveling with the spacecraft and for those inside. But would this hold true for another observer traveling in the opposite direction? According to Einstein's first principle, the principle of relativity, the observer can consider himself at rest. According to the second principle, the speed of the light will not be affected by the motion of the spacecraft. Spacecraft 13 with the bow and stern clocks moves by. The stern clock is triggered first because the stern of the spacecraft moves towards the approaching light wave. The bow moves away from it. Clocks which are synchronized for one observer appear unsynchronized to someone else moving in relation to him. Aboard spacecraft 13, the crew considers the ship at rest. The clocks are synchronized. To them, it is the other spacecraft which is moving. Again, the motion of the light wave will be independent of the motion of the ship. The stern clock is triggered first. In an object moving at high speed, the stern is always seen to be advanced in time. Each observer determines the order of events using his own time system. In this sense, time is relative. In this vastness, there is a star that we on Earth measure as 200 light years away. Leaving the star in 1776, light traveled for 200 years before reaching us. During this time, important events were happening on Earth. 1815, the Battle of Waterloo. 1905, Einstein's special theory. 1957, Russia launches Sputnik. When we say that something happens at a certain time, we mean that it happens at that time in our particular time system. To another observer moving in relation to our galaxy, the light leaving the star would have been simultaneous with a different event in Earth's history. To this observer, the Earth and the star can be thought of as one system, like the two ends of a moving spacecraft. Earth, as the stern clock, will be ahead in time. When it is 1776 on Earth, the observer sees an earlier time on the star. On Earth, they say the light leaves simultaneously with the calendar reading of 1776. To the observer, the events are not simultaneous. Einstein realized that all judgments of time involve judgments of simultaneous events.
In some cases, the order of events is arbitrary. Let me explain. Suppose here's an event A, and there's another event B. It can happen that everybody agrees that B is after A, or it can happen that everybody agrees that B is before A. However, in relativity, there's a third category. I can have an event A and an event B, and while I think that B occurred after A, someone else moving relative to me will think that B occurred before A. And this particular third category of events that you can't quite tell which is first, which is second, that does not exist in Newton's theory. It's a very essential thing in Einstein's.
This insight about the order of events led elsewhere.